Hello, I am Mason Cipollini, joined by Colin Brown and Leif. This is Lab 7 for OPTI 471b.
To introduce this experiment, we review three key concepts from diffraction theory: the point spread function, the line spread function, and the modulation transfer function. The point spread function, or PSF, describes how a point source is imaged. Instead of remaining a perfect point, it spreads due to diffraction and aberrations. The line spread function, or LSF, describes how a line is imaged. Since a line is a collection of point sources, the LSF is the sum or integral of the corresponding PSFs. Finally, the modulation transfer function, or MTF, describes how image contrast varies with spatial frequency. Often in line pairs per millimeter, it is the normalized magnitude of the Fourier transform of the LSF, where AC and AS are the real and imaginary component. A diffraction-limited system produces the smallest possible point spread function. Aberrations increase this spread, so if they are negligible, diffraction sets the fundamental limit. The MTF can be compared to a theoretical diffraction-limited MTF to assess system performance. The cutoff frequency is where the MTF goes to zero, meaning no contrast is transferred. Diffraction determines this limit. It sets the highest resolvable spatial frequency. Finally, the area disk is the diffraction pattern from a circular aperture. The Rayleigh criterion states that 2 points are just resolved when the peak of one aligns with the first zero of another, giving a minimum resolvable spot size of 1.22 lambda f number. When two light paths differ by lambda over 2, they acquire a pi phase shift and interfere destructively, producing a dark region. A difference of lambda gives a 2 pi phase shift and constructive interference, producing a bright region. For a circular aperture, we compare a ray passing straight through the center with one that passes through a point Q in the aperture and then diffracts to a point P. The OPD between these paths can be approximated as rho a squared over 2L, where rho a is the radial distance of point Q from the optical axis, and L is the effective propagation distance. This quadratic dependence of OPD on radius leads directly to the structure of diffraction patterns, as we will see next. Building on the OPD expression, we can predict the diffraction pattern at point P for a circular aperture. The result is a series of concentric rings of constructive and destructive interference, known as Fresnel zones. Each zone is defined by a lambda over 2 change in optical path difference. The Fresnel number, NF, corresponds to the number of zones, M, contained within the aperture. These zones have two important properties. Their radius increases with the square root of the zone number, while each zone has approximately equal area. In this experiment, we will intentionally configure the system to observe different diffraction regimes corresponding to m equals 0, m equals 1, and m equals plus 1.
Alignment here is identical to last week. Align the laser with the sliding pinhole, mark the beam location on a screen, adjust the XZ translations of a microscope objective until focused on the mark, and add and adjust the spatial filter with the objective until all fringes are visibly gone. Swap the filter stand for a collimating lens and adjust until retroreflections go into the laser cavity. With all rail 1 aligned, assemble the beam expander and look for parallel fringes on a shear plate to test collimation. Clear rail 1 for now, add a mirror on a rotation stage at the end of the rail and align it with the sliding pinhole like the laser on rail 2. Keep a pinhole near the mirror, place a test lens after it, and adjust until retroreflections go cleanly through the pinhole. Finally, replace the lens with a microscope tube and adjust until the crosshair and beam are aligned on the screen mark. Assemble the beam expander once again on rail 1 and replace the adjustable aperture on rail 2 before the microscope. Calculate the location Z2 where the Fresnel number will be 1 and move the microscope beyond that distance. Slide the microscope toward the aperture until the center dot of the spot is at its fullest intensity. That's where NF equals 1. Move the microscope closer until the center of that spot's ring is the darkest. That's where NF equals 2. Insert the 400mm focal length test lens before but close to the aperture and move the microscope to the lens's back focal length. Slide the microscope until the darkest spot center appears before and after the focus to find the plus and minus 1 wave defocus. Increase the radius of the aperture and relocate the positions of these waves of defocus for each adjustment. The average of these locations will give the best focus position. Finally, calculate the difference between the locations and plot them against their respective aperture sizes. Choose a viable spot size and calculate the necessary aperture size to create it. Use the microscope and a caliper to adjust the aperture to this specification. Measure the distance between the lens and aperture and calculate the f number and cutoff frequency of the new diffraction-limited system. Use the microscope to find the best focus, place the diffraction slit set upon an XY translation stage at this position and calculate the slit width. Then, replace the microscope with the power meter and take power readings as it is translated from one slit edge to the other with 10 micron micrometer increments. These power readings are then plotted against the respective micrometer positions to form the line spread function. This is repeated 2 more times, but instead for the plus and minus 1 wave defocus positions.
Moving on to results, first we look at D versus aperture size, where D is the axial distance between plus and minus 1 waves of defocus in the diffraction pattern. Here, we find an inverse relationship as expected. To measure the line spread function of our system, we first set up the diffraction limited system. Given the resolvable resolution of our micrometers, an area disk diameter of 200 micron is chosen. From this, and the focal length of the testing lens, we calculate the aperture diameter as 3.1 millimeters, and the slit width as 84 micron. These are validated using the microscope and its micrometer to measure the dimensions. For each of the axial positions of the diffraction patterns, the microscope position was found by observing the projected image on a screen and adjusting for best image. With microscope position set, the slit was brought into the same position by turning off the laser source and viewing the slit through the microscope. The slit was then translated laterally to scan the profile of the diffraction pattern. In terms of shape, we see great agreement with the Zmax theoretical plots, while we see some slight difference in scale. This is related to the difference in cutoff frequency explained in the MTF data. To find the MTF, our data was fed through the provided script. Here we find that the uncorrected curve provides the best agreement with the Zmax graphs, with a fairly well-matching cutoff frequency for all of the positions. The corrected curve appears to contain some artifact around the theoretical cutoff frequency of 11.8 cycles per millimeter. However, we believe this to be inaccurate, as the system modeled in Zmax shows a cutoff frequency of around 15 cycles per millimeter, which is closer to what our data shows.